Hello everyone, here is Carlo Andrea Biraghi, and today I'm going to talk to you about the IMM porosity key category. To make it, after a theoretical explanation, we are going to move on some example area in the city of Milan. We first move from a scientific definition, that is porosity or void fraction is a measure of the void or empty space in a material, and is a fraction of the volume of voids over the total volume, between 0 and 1, or as a percentage between 0 and 100. But what is the porosity key category composed of in IMM? It is made, as all the other key categories, by a layers ranked superimposition. It means that each single layer have a different role in the definition of a key category. In the porosity case, volume is the main one, followed by void, then link, and last is function, not affecting this key category. Our investigation process started determining porosity in terms of the void in a defined volume of a material. Then we look for some principle for outlining the volume of a urban context and define a calculation method of the porosity in a city, through a set of values as volumes, surfaces, footprint, distribution, and buildings. We improve the graphical representation, moving from a value to a porosity spectrum diagram, and then we analyze some area in Milano as case study. We also define some graphical representation of void space in relation to bit volumes and give you the instruction to repeat this procedure on your own. Like the sample described in the image, the porosity is defined by the volume of water that occupies the void space of the outlined specimen, here a sponge. The concept is clear, but how to apply this principle at the urban scale? To delimit the volume of the urban environment, we consider a concept from the processes of urban heat island, defined as the urban canopy layer, which is the warm layer of air near the ground. With this principle in mind, the boundary of the urban material would be a wave-like pattern of varying building heights. Under this definition, each context would be unique in urban morphology. However, due to the complexity of this boundary, the calculation of the total volume of urban material would be extensive and difficult to carry out. The scope of our investigation is to provide a simple method of calculation for the user. Therefore, we decided to use the average weighted height of buildings, xh, covering the area of analysis in order to define the boundary of the urban volume. So, xh is given by the area of building footprint multiplied by the height of building, and it gives the total built volume as a result, and then divided by the sum of total areas. After obtaining it, we can find the total volume of the selected site and the volume of its built area. After determining these values, we can calculate the volume of void space. So the total volume is given by the total selection area multiplied by xh, while the built volume is given by the area of building footprint multiplied by the height of buildings. The volume of void, in the end, is the total volume minus the built volume. Finally, with these values defined in the formulas mentioned before, we can apply the formula of porosity that gives us the percentage ratio as follows. So the porosity value of volume is given by the void volume over the total volume of the area. Until now, we considered porosity quantitatively, in relation to the volume. However, during our research, we discovered that the area of the surfaces enclosing the volume influenced in porosity qualitatively. Above, we present two samples of volume with voids. Although both have the same footprint and void area, the surface area of vertical enclosure is greater in the second sample than in the first sample. Therefore, our calculation method expands broadly considering this fact. We take our area of analysis and sum the total free vertical surfaces of the buildings. Then we make a ratio between SV in relation to the total area of analysis. SV is given by the perimeter of buildings multiplied by their height, while the total area is given by the built area plus the void area. Finally, with these values defined in the formulas mentioned before, we can apply the formula of surface ratio that gives us a percentage as follows. The surface value of porosity is given by the total free vertical surfaces over a sum between the total selection area and the total free vertical surfaces. Note that we are talking about free vertical surface, so not all surface should be included. The picture below tries to clarify this concept. In the first one, we have a 3D model, so showing all possible surfaces in the sample. Then we have surfaces not to be counted, that are the building footprint, the roof surfaces, and all the surfaces that are in between two buildings and so that are hidden in this picture. While in the last one we have the free vertical surfaces. The white and lighter red are the ones that we can directly see, while the darker one represent the backside of surfaces looking on the opposite part of the sample that otherwise won't be visible from here. Density is the third concept that is necessary to understand the morphology of a city. Density is usually considered as the ratio of number of inhabitants to the area of a site. However, the three diagrams above all have the same density, but their morphologies are different. Hence, to evaluate this variance, density must be complemented with other indicators. We need some values more linked to the urban morphology. For example, coverage can be expressed as the ratio of the ground floor area of the enclosed buildings in relation to the area of the site of analysis. And so our coverage percentage of porosity is given by the ground floor area over the total area. The gross floor area ratio, FAR, is the ratio of total building area to the area of the site of analysis, and the formula is given by the ground floor area multiplied by the number of floors of the buildings divided by the total selected area. In this case, FAR compared to coverage includes also the information about the height of buildings, and turns out different values. This value, the FAR, needs to be normalized dividing per n a number of representatives of the context to fit the spectrum diagram for selected case studies. For the city of Milan, we realized that this number could be 5, but I explain you this better in a while. Another factor that affects the morphology is the distribution of buildings. So from our research, we noticed that in similar area of analysis, we can have the same number of buildings, but different morphologies. Elements characterizing the urban fabric are the position and so the mutual distance between buildings. This allows us to define the concept of group, an amount of buildings within a certain distance. Here you can see 3 examples from the city of Tokyo, where the distances among buildings are really different, and in the end, all the buildings tend to be part of a single group or really divided in many different units. To identify this group, we have to perform an offset by distance t of building's perimeter and look for intersection of these boundaries. Overlapping areas have to be joined and counted as part of a single group. Repeating this operation until we find no more, we are able to see how many groups is the fabric divided in. The 3 pictures below show the same fabric but tested with the different distance of offset. In the first one, with a low distance of 4 meters, we still have 13 groups, so something that apparently doesn't have such strong relation among buildings. The second one, with a 10 meters that could be in many contexts a meaningful distance, show us the relationship among different buildings and group the fabric in 2 main areas, while the last one, with a really large distance of 20 meters, tends to include everything in the same group. This procedure returns an integer number that varies according to the selected offset distance. This distance needs to be determined for each city in order to show meaningful differences among areas. Considering it is mainly affected by distances, it has a relationship with minimum allowed street width of each context. For our selected case studies, we use 10 meters, while for the Tokyo picture in the previous slide we use a value of 6 meters. We tested, discovering that when distance tends towards 0, each building is a group, and when it tends toward infinite, for example as value higher than 100, one single group includes all the buildings regardless the study morphology. For our case study, we took a distance of 10, a measure able to show meaningful differences among morphologies. So in the end, the building distribution factor is only dependent by the number of groups identified in the area. For calculation purposes and graphical representation, we took this ratio and expressed it in terms of percentage in order to adapt it to our porosity spectrum diagram. To achieve this, we normalize and subtract it from the value 1, which represents the condition of all buildings belonging to the same group, a really homogeneous and continuous fabric. So, the porosity value of building distribution factor is given by 1 minus the number of groups minus 1 divided by 100. Theoretically, the maximum is equal to the number of buildings. In test, we found no values higher than 40. For extremely sprawled contexts with more than 100 groups, we'll obtain negative values to be returned to 0. Now we introduce a new concept called number of buildings. To explain it, even if it looks quite simple, let's look at the maps above, that are at the same scale. On the left, West Bay in Doha has few huge buildings, while in Venice, built volume is spread into many smaller buildings. This fact affects also void space in terms of number, shape, and size. To highlight this difference, we consider the number of buildings per hectare. The number of buildings value expresses the number of physical buildings in relation to the selected area of analysis, so buildings per hectare, number of total buildings divided by the total site area. However, to express this ratio in percentage and get values among 0 and 1, we normalize it, defining a maximum possible number of buildings based on a ratio between an upper extreme for coverage, for example 50%, and the lower extreme for average building footprint, 100 square meters. In the end, number of building porosity value is given by the number of buildings over the total selection area divided by 50 in our case study. Real extreme cases may require a higher one, that will almost never be higher than 150. It is representative of a 75% of coverage and the 50 square meter as average building footprint. Finally, we represent the 6 indicators in a porosity spectrum diagram, which is composed of axes that contain the measurements up to a maximum value of 1. This diagram is clear to visualize, since it can also be used comparatively between different case studies. The following slide presents 3 case studies of porosity investigation in different neighborhoods of the city of Milan. As you can see from the diagram, it can be useful to look at these simple lines to grasp some intuitive difference among neighborhoods even before looking at their maps, that I'm going to show in a while. The first one is the historical city center of the city of Milan. It is a consolidated part characterized by many closed courts, often of small dimension, and narrow streets. This part of the city was the one previously included in the perimeter of defensive historical walls. As we can see from the diagram, all the values are quite balanced except for the building distribution factor that reach almost the value of 1, and it means that this fabric is really homogeneous and really continuous, and we don't have such strong exception in it. And also the street width is small enough to allow buildings to establish a relationship among them. Then we move to the area of Città Studi. It is still consolidated and represented by a grid and diagonals system and by the presence of the university campus of Politecnico of Milano. Comparing this diagram with the previous one we have seen, we can see an increase in volume, also thanks to the picture on the left, and the reduction by consequences of the distribution factor. Also the FAR is reducing because the building height is not increasing compared to the city center, and the increasing of volume make the coverage value even lower. Finally, we get to the area of Porto di Mare, that is a peripheric one, where city passes from urban to rural landscape. It is characterized by the isolated linear buildings, typical of modern movement, and huge large voids, mainly due to the presence of agricultural fields or also to brownfields. The diagram is really more irregular than the one we've just seen before, and the volume of void, is characterizing its shape, while all the other volume represent an area that is not so densely built. After many different attempts to find a synthetic representation for porosity key category, we realize that the physical appearance and consistency of the city is the best way to express it. Each of the 6 values included in the spectrum diagram may have its own visualization for a better understanding of the concepts, but they won't be so representative of the general concept. Now we move to the more practical part of input data and procedure, how to do this analysis. Now that we understood the theory, it's time to apply it. All these analyses can be made by hand mapping the required informations, but it's more convenient to rely on existing data sets and to use specific software for the calculation. 2 alternative sources can be local topographic database, the one we use in this case, and for example for the area of Milano or Lombardy in general, you can refer to geoportale.regione.lombardia.it, or for the Milan area, geoportale.comune.milano.it open data. or the OpenStreetMap data, that are a really powerful tool but not yet ready for all contexts. The home page is openstreetmap.org, and another link that you can directly follow by this home page is city extracts called mapzen.com/data/metro extracts. It allows you to get already some cut of different cities around the world. Useful software are GIS, Excel, and Grasshopper, especially for building distribution factor calculation. According to the data structure and level of detail, some cleaning or filtering operation could be needed in order to provide more reliable results. These operations have to be made with GIS or directly in Excel and are not so complex. All information are normally inside the DBF or CSV file attached to the SHP when downloading, so all the calculation can be made directly with a simple Excel sheet. In case we have to extract data from simple drawings, some automation with Grasshopper or GIS are suggested. For building distribution factor, we wrote a simple algorithm with Grasshopper using the component Bowerbird offset from Bowerbird plugin. Required information and data to run analysis are so: building perimeter, a closed polyline for each different buildings, so a curve; building height, value expressed in meter; building perimeter, the length of the previous mentioned line expressed in meter; building area in square meter, and the total selection area, always in square meter. Area and perimeter may be extracted from the polyline and collected in a chart, or directly processed within Grasshopper. Height can be obtained consulting maps containing this information, or from a 3D model if you have it. All the calculation may be done directly in with an Excel file, but building distribution factor and surface require a preliminary graphing investigation. Here a possible template. Here we have a row from Bergamo Alta input data. The first three are input values, the one we mentioned before, while the other can be easily obtained from them through simple formulas. A chart, as the one on the left, can represent the final result of the investigation. Where you here see the values, there are the formulas behind, previously showed in the theoretical part. The chart could be also useful to show the same result of the spectrum diagram, but in a different way. So that's it. Thank you for your attention. I hope you enjoyed the tutorial, and if you're interested in learning more about IMM, visit the website immdesignlab.com or follow us also on Twitter. Bye.